So, BTEC Applied Science for AAQ. This chemistry video, Unit 2 Chemistry, is about rate equations. So, in this video, I'm going to talk about rate equations and what they are. It's not the equation for the reaction. This is a rate equation. It's how we work out the rate of reaction. I'm going to talk about orders of reaction, and I'm going to talk about rate constants and their units, which you need to know. As ever, I don't do stuff that you don't need to know. Okay, there's one or two comments on my website. Do I need to know this? Well, if it's in my video, then yes, unless I say otherwise, which I very rarely do. Anyway, let's get on with it. So we've got a reaction. So A plus B goes to C plus D. So my reactants are A and B, my products are C and D. Now, how does the rate of reaction depend on the concentration of A? And for the concentration of A, we put it in these square brackets, yeah? When we see that, that means the concentration of A, where A might be sodium carbonate or calcium chloride or whatever. Now, here are some possibilities. So look at these graphs. The first graph, how does the rate depend on the concentration? And the answer is it doesn't, does it? You change the concentration, the rate stays the same. The second graph, well, it's a straight line, and that means that the rate is proportional to the concentration of A. And then on the third graph, it looks as though that the rate is more than proportional. Yes, if we increase the concentration of A, if we double the concentration of A, then the rate more than doubles. So, look at this. On the first graph, the rate does not depend on the concentration of A, and we write that as that the rate is proportional to A to the naught. Yeah, A in brackets to the naught. Anything to the power of 0, you should know, is 1. Okay, 5,000 to the power of 0 is 1. So basically, the rate doesn't depend on the concentration of A. We call that a zero order relationship. On the second one, the rate is proportional to the concentration of A. So the rate is proportional to A to the power of 1. In other words, the rate is just proportional to A. Yeah, it's a proportional relationship. And we call that a first order relationship. On the third one, in this particular case, the rate is proportional to A squared. Yeah, the concentration of A squared. In other words, if we double the concentration of A, then the rate is 4 times bigger. If we treble the concentration of A, then it's 9 times bigger. We call that a second order. So 0, first order, second order, and you'll see that matches up with the indice, yes? So 0 order, that's like to the power of 0. First order is to the power of 1. Second order is to the power of 2. So these are some possibilities for the relationship between between the rate of reaction and the concentration of A. Now, the same thing will apply to B. The rate of reaction may well, probably will, depend on the concentration of B. So if I want an equation for the rate of reaction, it'll probably include both of them, and it will look something like that. So the rate equals a constant, concentration of A, I've said to the power of m, concentration of B to the power of n. Now, let's explain this equation. So, equals a constant, yeah? Whenever you see is proportional to, that little fishy looking thing, you can replace it with equals a constant, okay? And K is called the rate constant, and that is a constant for this particular reaction. M and N are the numbers we were talking about before. In our case, it'll either be 0 or 1 or 2. In fact, if it's 0, then it won't even turn up in the equation, will it? Because the rate doesn't depend on it. So it'll either be 1 or 2, and if it's 1, we just don't bother writing it. Yeah, so K is the rate constant for the equation, for the reaction, beg your pardon. M is the order for A, N is the order for B. I've seen different letters used for that. I've seen X and Y. I've seen little a and little b. In the revision guide that we use, it's M and N, so that's what we're going to use. Okay, so the rate equals a constant, yeah, times the concentration of A to some power, times the concentration of B to some power. The overall order is M plus N, and that will be important later on. Knowing what the overall order is, you just add them together. So here's a nice simple little question for you to have a go at. The rate equation for the reaction between nitrous oxide and oxygen is that. Have a read, have a go yourself, and then I'll go through the answers in 3, 2, 1. So, what would happen to the rate of reaction if we double the concentration of oxygen? Now, looking at the equation for oxygen O2, that's first order, isn't it? Yes, because there's no indice there, there's no power there, so that's O2 to the power of 1. So the rate is proportional to the concentration of oxygen. If you double the concentration of oxygen, then the rate will double. What would happen if we double the concentration of the nitrous oxide? Well, it would be 4 times bigger. Why? Because that is a second order. Yes, it's NO to the power of 2. And that means if we double the concentration of nitrous oxide, then it would be 4 times bigger. The rate would be 4 times bigger. What does the value of K depend on? In the last video, it depends on temperature. It depends on pressure. It depends if a catalyst is being used. I'm saying these because they're both gases. Nitrous oxide and O2 are both gases. So pressure, it will depend on pressure. Okay, now, looking at this, the values of the orders are determined by doing experiments. So we do experiments to find out the order, yes, for each of the reactants. And what you do in these experiments, in this table, 1, 2, 3, 4, 5, is you change the concentration of one of the reactants independently, and you see what effect it has on the initial rate. Yeah, the initial rate is when you do concentration against time. It's the gradient at the beginning, isn't it? Yes. So what effect do they have on the initial rate? You have a look at the table yourself and see if you can figure it out. See if you can write a rate equation for this reaction and see if you can figure out what the missing value is. And I'll show you the answer in 3, 2, 1. So rate equals K, so concentration of A squared times B. Why? Well, the first thing to note is that the rate doesn't depend on C. If you look here, I'm doubled the concentration of C. I've kept A and B the same. This is in experiments 1 and 2. A and B is the same. I've doubled the concentration of C, and it hasn't had an effect on the rate. So for C, it's 0 order, so that doesn't come into the equation. Yes? What about for, if we look at A, now when I double the concentration of A, so that is from, let's have a look, so from 1 and 4. So from 1 and 4, that's 0.1, 4 is 0.2, but B is the same. So B is 0.2 in each case. So doubling the concentration of A, what's happened to the rate? It's 4 times bigger. We've gone from 4 to 16. And that means that A is a second order. The indice, the order, is 2, equal to 2. What about B? Well, if we look on, C doesn't matter. If we look on columns 2 and 3, for example, the concentration of A stays the same. If we double the concentration of B, then the rate doubles. And that suggests that the rate is proportional to the concentration of B. So that's first order. So my rate is K times A squared B. Yeah, concentration of A squared times concentration of B. Suggest what the missing value in the table is. Well, the missing value is 32. Why? Because to get to experiment 5, we've doubled the concentration of A and we've doubled the concentration of B, haven't we? So it's going to be twice as big, yeah, times 4. So it will be 8 times bigger, so 4 8s are 32. Notice how the zero order term, which is C, doesn't appear in the equation. So well done if you've got that. Moving on. What are the units of K? This is something that you need to be able to figure out. And it depends on the overall order. Okay, now remember that the rate, what are the units for the rate? Well, they are moles per decimeter cubed per second. When we get the gradient of the graph, it's the, let me change my pen color, it's the change in concentration divided by time. So the change in concentration is moles per decimeter cubed divided by time, so per second. So moles per decimeter cubed per second. Those are the units for the rate. Now, that's in our head. Let's go to the next slide. Now, how do we work out the units of K? Well, the trick is that in our rate equation, we've got to have the same units on both sides of the equation. This actually goes for any equation in science. You've got to have the same units on both sides, or equivalent units on both sides. Look at the first one, the first order. So looking at the first order, we have the rate is K times the concentration of A. So let's put in the units. Yeah, so rate is moles per decimeter cubed per second. Yeah, just did that on the last slide. On the other side of the equation, we've got the units of K times moles per decimeter cubed. So let's do a little bit of cancelling. So that moles per decimeter cubed will cancel with that moles per decimeter cubed. And that gives us that the units of K, seconds to the minus 1. So for a first order reaction, if the overall order is first order, the units of K are seconds to the minus 1. Second order is a little bit trickier. We'll do the same thing again. So on the left, we've got moles per decimeter cubed, seconds to the minus 1. On the right, we've got the units of K times moles per decimeter cubed squared. Now, what's going to happen here, if we do our cancelling, is that moles per decimeter cubed will cancel that square there. So that square will disappear. So what will the units of K be? Well, it will be seconds to the minus 1 divided by moles per decimeter cubed. Now, because it's divided by moles per decimeter cubed, then it's seconds to the minus 1 times moles to the minus 1 decimeters cubed. Yeah, you notice that it becomes per mole and decimeters cubed. Yeah, there you go. See if you can work out the other one. See if you can work out third order, fourth order. If you can, I'll be impressed. Go for it. And the answers are in 3, 2, 1. There you go. If you manage to do them, brilliant. It's the same logic. I just put the units on both sides of the equation. I did a bit of cancelling and I figured out what the units of K are because it's the same units on both sides. If that's too much for you, then you either say, well, I'm not going to get that mark, or you learn the units of K there for first order, second order, third order. Maybe there's a little trick for figuring it out, for working it out, a sneaky shortcut. Anyway, figure it out yourself. Right then, it's been quite a challenging video, lots of stuff in this video. If you can do these questions on this slide, well done. Okay, have a read, have a go yourself. I don't think you're not going to get anything harder than this. Do it. And I'll show you the answer in 3, 2, 1. So, the equation for the reaction sodium carbonate and hydrochloric acid is blah. So your sodium carbonate, your hydrochloric acid are both aqueous. Yeah, they're both dissolved in water. We do some experiments and we're changing the concentration of this, that, and the other. And there's our results from our experiments. Okay, which is the correct rate equation for this reaction? Well, looking at the table, if we double the sodium carbonate concentration, then the rate doubles. So my sodium carbonate is first order. Also, if we double the hydrochloric acid concentration, then the rate doubles. So my hydrochloric acid is first order as well. So the answer is that one. They're both first order. So my overall order is 2, is second order. Predict what the rate will be in the last row of the table. So if we double both of them, it will be 4 times bigger. So 4 times 4.38 is 17.52 times 10 to the minus 6. Times 10 to the minus 6. Predict what the rate will be in the last row of the table. I've just done that. Anyway, moving on. Use data from any row in the table to calculate the value of K. So I've used the first row of the table, and now that I've got my rate equation, yes, I can just work out the value of K. It's the rate, which is in the table, divided by the concentration of sodium carbonate times the concentration of hydrochloric acid. So my rate constant is 7.01 times 10 to the minus 3. What are the units of that? I'm not going to go through all the cancelling business. I just remember that if its overall order is 2, then the units of K are moles to the minus 1, decimeters cubed, seconds to the minus 1.